Okay, here's another example of an optimization question, and you're given that you have a closed rectangular box with a square base, and it has a volume of 64 cubic meters. And you're asked to find what dimensions, in this case length, width, and height, will minimize the surface area. So I will try to draw a rectangular box, and I do apologize in advance, but essentially you've got something that looks like this, and again, it's very bad, I apologize, but this is your rectangular box. Now it says that the volume is 64 and has a square base, so the length, say x for if you want, and width are equal, and I can let y equal the height. So the volume of a rectangular solid is length times width times height. If you want, v is equal to x squared y. And we know that the volume is 64, so x squared y is equal to 64. And if we solve for y, which we can do now or later, y is equal to 64 divided by x squared. And we notice the question, it asks you to minimize surface area. So the surface area, say for example A if you want, or S, it's the area of the base, which is this area here. So it's x squared, and there was a top and a bottom, so there are two of these, plus the area of one of the sides, the front here. Again, I apologize for the drawing, but the front here, it's again a rectangle, and that area is x times y, and there are four of those. And as with all optimization problems, you try to get the quantity you're using in terms of one variable. So what we're going to look for is a of x. So what I can do is replace this y with this term right here. And that will give me the surface area A, or S if you wish, as a function of x only. So a of x equals 2x squared plus 4x. Y is 64 over x squared. And you can simplify it. Area as a function of x is equal to 2x squared plus 256 over x. And this is the equation we're going to use. Okay, so we have the equation in terms of one variable only, in this case is x. And now we differentiate that derivative equals 0 and solve for x. And that will be our answer for our length and the width. Substitute in, we'll find y, our height, and verify. So the derivative, which is a prime of x or dA dx, doesn't really matter what notation you use. A prime of x is equal to 4x minus 256 over x squared. And again, as an example we saw yesterday or previously, the derivative of 256 over x, which is negative 1, is negative 256 x to the minus 2, which is minus 256 over x squared. So in case you're wondering where that came from, that's where it is. And now we let this derivative equal 0. Messy, hopefully you can make it out. So we have 4x minus 256 all over x squared is equal to 0. And we could say that 4x is equal to 256 over x squared. If you want to cross multiply, you certainly can. 4x cubed is equal to 256 divided by 4. X cubed equals 64. And we're given that x is simply a cube root of 64, which is 4. That is our length. We also said, we go back to the drawing, such as it is, it's a square base, so the length is 4, the width is 4, and we said that y, if you recall, was 64 over x squared. So it's 64 over 16, which is 64 over 16, which is also 4. So the dimensions are 4 meters by 4 meters by 4 meters. And the only thing you have left to do is actually verify that it is a minimum. So we'll find the second derivative, a double prime of x. And we go back, so we'll differentiate this term here. And we're going to have 4 plus 512 over x cubed. And you can verify this derivative here if you wish. Right, but that's all we get. And this is always greater than 0 when x is equal to 4. So we've actually verified it. So we've got the dimensions. It's a 4 by 4 by 4 rectangular solid. And we've actually verified that it is a minimum. Since it's greater than 0, we know it is a minimum. And we've solved the problem.